Hi, today we're going to go over shear stress, and we're going to graph the shear stress throughout this I-beam right here. So the question really is the question would be graph the shear stress of the steel beam. So in order to get the shear stress, right, let's go over what we need. So for shear stress, our formula is going to be that Q, actually, sorry, it's not Q, it's tau now, is equal to VQ over I. That actually would be giving you shear flow, and then T makes it shear stress. Okay. So we are given that the V is equal to 250 pounds, right? And we'll solve for our moment inertia. Our inertia, I, is equal to 112 pH cubed minus the second pH cubed in parentheses, which then is equal to 112 8 10 to the third minus the smaller rectangle, which is 7 8 to the third, and that is equal to 368 inch to the fourth. All right, so we know that tau is then equal to V Q I T, where V and I are now known, 250 over, it is 368, which is then equal to 0.68 QT. That just makes our calculations easier because we've eliminated the V and the I, and we just have a constant number to represent. And all we're going to be doing now is just solving for Q and T. All right, so in order to do it, we've got to look at every section. And so the best thing to do, I'm going to do is copy. I'm going to paste this. We're going to be looking the shear stress at the very end here is 0 because it's at the edge of it, right? So we know that tau at 0 is equal to 0, right? And then we're going to move on to this, which is going to be tau of 1, and this is tau at 0. So tau at 1, we're looking at that, and then we're solving for Q. Now Q is going to be that area, and the distance is going to be half of that since this is 1 inch thick, right? And then that's going to give you 4 to here. Let's say that this is a center line. We've got 4 inches there. So half of that is going to be, so in other words, your Y bar is equal to 4.5 inches. So we've got 0.68. Okay, sorry. Oops, wrong problem. Oops, sorry. Tau 1 is then equal to 0.68 Q, which is the area times its distance. The area is going to be 8 times 1, so 8 times 1, and then y bar, which is 4.5 inches, divided by t. Now the thickness of that top one is 8. And so what you would get there is that tau is equal, tau at 1 inch is equal to 3.06. PSI. Now, I'm going to do that as 1A, and then we're going to have tau 1B, because the thickness at, let's zoom in, right? So the shear flow is at this point right there. So at this point right here, right? At this point, the thickness is either this, or right here is 1 inch, right? It's either 8 inch wide or 1 inch wide at this point, right? Because theoretically at that point, like the 8 and the 1 inch are at the same line. So we have to solve for it, and you'll see that our diagram will jog to account for it. So that's equal to 0.68. The Q is the same, 4.5. The difference is that that becomes 1 instead of 8. So you'll get that to be increased to 24.48 PSI. All right. So now all we're going to do now is we're going to start incrementing. Now what's really cool is that once we're past this line, we're just going to be starting to increment, right? So that would give us, so we're at 1 inch, that's 2 inch, that's 3 inch, that's 4 inch, and then 5 inch essentially would be where we would stop, right? Okay. So let's keep on going. Okay, what I'm going to do is I'm going to copy, paste. We're going to now solve for tau. That keeps on coming up. Tau at 2 inches. Where's that located? Where? Here's 1 inch. Here's 2 inches. Right, we have 0.68 Q over T. Right, we know what's really cool is that moving forward, T is going to be 1.0, right? So we could just say that it's going to be 0.68 Q at this point. Now, what is Q? Q is going to be what we had, and really the thing is, the best way to do it would be to just include that portion that we're looking at right now. Okay, so what's the area of this? Well, the area is going to be 1 times 1, right? And what is y bar? Well, y bar is going to be half that distance to the center line of that beam. We know that it's going to be right. What is that distance? Well, we know halfway is 5 inches, so we're going to minus 1, it's 4 inches, minus 0.5 is 3.5. Right? So Q is going to be area, which is 1 times 3.5. So what we have then is we're going to actually take what's above, we're going to add it here, 24, we're going to add 0.68, and it's going to be 3.5. And I'm just shortcutting 3.5. Why? Because Q is equal to area times Y bar. Area is equal to 1.0, so we're just looking at Y bar now. And that is equal to 26.18 psi. See what we're doing? All right, so tau at 3 is equal to 0.68 Q, really. And what we're going to do is we're going to copy this again. Let me see if I could just keep on pasting this. Because we're in a 3, 4, and let's do 5 over here. I know it's not like the best, but okay. So we're at tau 3, which tells us that we included the 1 inch, 2 inch, 3 inch, right? And so we really just have the previous value, which is 26.18 plus 0.68, and essentially we're looking at that right there. We have the center line. What is the Y bar? The Y bar is 2.5. Multiply by 2.5. I'm just gonna put 1 in there for just in case it bothers you. And so we have tau 3 is equal to 26. Let's see, tau 3. Let's see. 27.2 psi. Okay, and then we're going to go to tau at 4, which is another 0.68 Q. We're going to take this, we're going to add that, 27.2 psi, and guess what now? Okay, so we did this, it's 1 inch, 2 inch, another 1 inch actually, right? This gets us at 3 inches, and this gets us at 4 inches, right? So we're looking at this block, that to the center, that distance is going to be 1.5. So it's going to be 0.68 times 1. It's well, let's see. Q is equal to A times Y bar, right? So area is 1.0 times Y is 1.5. And that is equal to, let's see. Let's see, so it's pretty minimal in terms of the increase. It's 0.68, 1.0. So I think two-ish is what we would be getting. And then finally, tau 5 is going to be the previous one, which is 28.2, and plus 0.68 times 0.5, because Q over Y bar is equal to, Q is equal to A times Y bar. Area, again, is 1.0, and Y, and we said that it's this one now. This last segment right here. There to there is 0.5. So we have 0.5 there. We find out that that value is 28.2, 0.68, 0.5 times. It's really not that much of a difference. And I might have done some numerical calculations somewhere along the lines. I hope I didn't. But what you can see is that as we get to the center, the increments start to slow down, right? Because you don't have that distance to multiply it out. So really what we're trying to do by doing all this stuff is we're trying to get the final value. So if I'm doing this correctly, let's make sure. Okay. All we're doing now is we would be graphing it. So if you have our I-beam, let me just do a fresh sheet. Our graph should look something like, it's parabolic, right? Shoots up straight, remember where this occurs? Shoots up straight, and it'll mirror here, shoots up straight. I'm probably exaggerating. And it's parabolic by that much. So I think for just graphing it, we kind of know what everything is in the way. So we know that the max, we're saying it was around 28.5. We also know that this obviously is 0. What we want to know is what this was, because it changes. And that's where you got 1A and B, 3.06 and 24.48. And if you did this much work at this point, I pretty much understood that you did everything. But if you wanted to go ahead and put in the values at the increments, you go 1, 2, 3, 4, and you could write those values in. And that would be graphing your shear stress diagram on the member. Now, remember that stress in shear is maximum at the center. Remember, in bending, stress in the middle was 0 because you had your neutral axis. So it's a little different, okay? All right, so that concludes this problem. Thank you.